What if I were to ask you, which would you prefer? Would you prefer to receive $1 today, or would you prefer to receive $1 1 year from now? Well, your choice between those two alternatives depends on the following. If we assume that given that we give you $1 today, you could invest that dollar and earn an interest rate, say R, per year, then you would prefer to receive $1 today rather than to receive $1 a year from now. Why? Because if you received $1 today, and invested it in that interest-bearing account in which you were earning this interest rate per year, then 1 year from now, your $1 would be equal to your original $1 plus the interest you've earned on that $1, which is just the same thing as saying your $1 would be worth this much. So you'd rather get $1 today than $1 a year from today, under the assumption that you could invest $1 and earn a positive rate of interest. Because then a year from today, you would have this much money, and you would prefer that than just getting $1 a year from today. The only way to get this money right here is to get the $1 today. So there's a time value to money, but only, the critical thing is only assuming that you can take the money you get and invest it at a positive interest rate. If you can't do that, then there is no time value to money. You're indifferent between receiving $1 today or $1 a year from today if you cannot take the $1 received today and invest it and earn any rate of return. So we're going to work through 6 equations that are the fundamental equations to the time value of money. And all 6 of these equations depend on that assumption that you can earn a positive rate of return R. So we're assuming there are 2 critical assumptions. We're assuming, number 1, that you can earn interest rate R, which is bigger than 0, per compounding period. Per compounding period, that means that you earn this interest rate R every time interest is computed or paid. That's what per compounding period means. And then the second assumption is that we're certain about that rate. So it's not like we have some uncertainty regarding this rate. It's not like we're assuming that you can earn a rate of 8% with 50% probability, and then 10% with 50% probability, and negative 10% with... But we're not doing that. We are certain. We are certain that you can earn whatever this rate is. It's a positive rate, and we're 100% sure that you're going to earn that rate. That's what certain means. So those are the two assumptions. And assuming those two assumptions, there are 6 equations that we can work through. And they are the fundamental equations and all time value of money concepts you can think about using one or multiple of these 6 equations. So the first equation, we're going to compute the future value of a single amount. We're going to call this single amount P. We're going to assume that you invest it once right now. So if you invest it once now, let's assume we're at the beginning of a period. Then at the end of the first period, what's your account worth? So the future value at the end of one period would be equal to, well, you'd have your P that you invested plus the interest you got over that first period on the investment. So the account would be worth this, just using the concepts up there. In this case, instead of $1, we're just saying P in general. Now P could be $1, it could be $50. But in general, if you put P dollars in at the beginning of the first period, aka right now, then at the end of the first period, the account will be worth this much. What about at the end of the second period? At the end of the second period, well, you would have what you had at the end of the first period still, of course, plus any interest that you earned on that over the second period, because in period 2, you're also earning an interest rate of R. R is the interest rate you earn per compounding period. And of course, what's common to both of these? We can pull a P times 1 plus R out. So P times 1 plus R times 1 is the first term, and P times 1 plus R times R is the second term. But here we have P times 1 plus R squared. After 3 periods, how much is your account worth? Well, after 3 periods, you would definitely have what you had at the end of 2 periods, plus the interest that you earned on that over that third period. And interest is earned at a rate of R. So at the end of the third period, your account, what's common to both of these terms? A P plus 1R, a P times 1 plus R squared, and we multiply that by 1 plus R, which is the same thing as P times 1 plus R to the third. So after 3 periods, the future value after 3 periods is this. And you can see the pattern. So after n periods, your account would be worth the initial P that you put in times 1 plus R to the power of n. This is the first time value of money equation. It's the future value of a single amount. This equation gives you the value after any number of periods where we're letting n equal that. This equation gives you the value of an account where you put P dollars in at the at the beginning of the first period, this equation gives you the value of that account at the end of any period after that. Now, we did make a jump between here and here. It just looks like the pattern is future value after the ith period is equal to p times 1 plus r raised to the power of I for all I, including when I equals n. But we've made a little jump here. Technically, we would need to prove that the pattern holds for all n. And to do that, we would do a proof by induction. But I'm going to omit that proof here. It's just a few lines, but it establishes mathematically, without skipping any steps, that we can go from 3 all the way to n, that it holds for all n. But I omit that. Just trust me, it holds. So, that's the first equation. What about the future value you have to forgive me, my tablet stylus program messes up sometimes, so I'll erase sometimes when it messes up. It puts marks on the screen that I don't actually put myself. What about if we have the future value, instead of investing that $P once at the beginning of the first period, we invest P at the beginning of every period. So at the beginning of every period, we put P into the account. What's the future value of that account? Well, after one period, we would have our P plus the interest earned on our P. So our account will be worth that much. After 2 periods, what's the value of our account? Well, after 2 periods, let's think about this. At the beginning of period 2, we put an additional P in. At the end of period 2, that P that we put in at the beginning of period 2 would earn interest. So we would definitely have this in the account at the end of period 2. But we would also have this right here, because that's what was in there at the end of period 1. So we're definitely going to have that in there at the end of period 2, plus the interest earned on that over period 2. So if we do a little algebra here, we have P times 1 plus R plus P times 1 plus R plus R times P plus 1 times 1 plus R, which is the same thing as P times 1 plus R times 1 plus, well, let's be careful here. P times 1 plus R. And then here we can factor a P times 1 plus R out. And we have that. This is the same as P times 1 plus r plus p times 1 plus r squared. And that's the same thing as p times 1 plus r, and then 1 plus 1 plus r, like this. What's common to these two terms? Simply this term. Go pull it out, and then multiply this by 1, that gives this term, and then multiply this by 1 plus r, and that gives this term. So after 2 periods, our account is worth this much. What about after 3 periods? Well, after 3 periods, keep in mind at the beginning of period 3, we put in an additional $P. That earns interest at a rate of R during period 3. We definitely have this in our account at the end of period 3. But we also have all of this in our account at the end of period 3 as well, because that was the balance at the end of period 2. And we have the interest earned on that. We have all of this in our account at the end of period 3. So if we just do a little algebra, this becomes P times 1 plus R. I'm going to multiply this through again. We're going to go backwards. So P times 1 plus R times 1 is that. Plus P times 1 plus R times 1 plus R is P times 1 plus R squared. Plus R times P times 1 plus R multiplied by 1 is itself. And then finally plus R times P times 1 plus R times 1 plus R, which is R times P times 1 plus R squared. And then let's see if we can simplify this. So I expanded it all the way out. Now let's simplify it. I think this term and this term have a P times 1 plus R in common. We have this term here, and then those two terms, this one and this one, let's factor out the P times 1 plus R, and then we have 1 plus R here, like this. So this is these terms added together. And we already have this term right here. Now we need these two terms added together. So plus let's think. Those two terms, these two terms here, have in common the P times 1 plus R squared. So factor that out, and we have a like this. So we've simplified. And now, what's common to all three terms? There are 1, 2, 3 terms here. What's common to all three of them? A P times 1 plus R. Pull that out. What do we have inside here? I'm going to put brackets just so we can see it more visually and not get lost in the parentheses. We pull out a p times 1 plus r from term 1. We got to put a 1 here. We pull out a p times 1 plus r from term 2. We have a 1 plus r here. And we pull out a p times 1 plus r from term 3. And we got to put a 1 plus r squared here. So after 3 periods, the future value of our account, p times 1 plus r, times this quantity, 1 plus 1 plus r plus 1 plus r squared. After 2 periods, our account was valued at p times 1 plus r times the quantity 1 plus 1 plus r. After 1 period, our account was valued at p times 1 plus r times the quantity of 1 plus nothing, right? So you see there's a pattern here. So it seems like then at the end of, after n periods, so after n periods, if the pattern stays the same, our account should be worth p times 1 plus r times the quantity 1 plus 1 plus r plus 1 plus r squared plus plus 1 plus r to the power of n minus 1. Right? Because the last exponent here is always 1 less than this number. See? There's an implied 1 right here. And that is 1 less than this number. And then up here, there's an implied that's the pattern. We don't need to go back to there. But that is the pattern. So if the pattern keeps holding after n periods, we should have this formula. Now, I do need a proof by induction to prove that we can move from this step to saying this. Because the pattern may break down somewhere in between there. But trust me, it doesn't. If we use a proof by induction, we could prove that the pattern maintains, and we do get this. The problem here is what's inside of the brackets. You see? All this. We need to find a simpler expression for this if possible. Because if n is big, like say n is equal to 100, then we have to write out 100 terms here. Right? 1 plus 1 plus r plus 1 plus r squared all the way to plus 1 plus r to the power of 99. That's 100 terms. And that's going to be very cumbersome. So let's see if we can find a simpler expression for what's inside the brackets. So can we find a simpler expression for what's inside the brackets? So let's let S be what's inside the brackets. Let S be the 1 plus 1 plus r plus 1 plus r squared plus 1 plus r to the third plus plus 1 plus r to the power of n minus 1. And let's do this to S. So in mathematics, S is a geometric sum. And there's a trick that's been known for a long time in mathematics. We can express S more simply if S is a geometric sum, which it is. And the way to do it is multiply S by 1 plus R, and then subtract S. What do you get? So multiplying S by 1 plus R, you get 1 plus R, 1 plus R squared, plus 1 plus R to the third, plus dot, 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 dot. And then multiplying this term by 1 plus R, you get just 1 plus R to the power of n. 1 plus R to the power of 1 times 1 plus R to the power of n minus 1, you add the exponents, equals 1 plus R to the power of n. So what you see here is 1 plus R multiplied by S, and now subtract S from that. And S is up here. So minus 1 plus R, minus 1 plus R squared, minus 1 plus R to the third, all the way dot 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 minus 1 plus R to the n minus 1. And notice that a bunch of terms cancel. This term cancels with this term. This term cancels with this term. This term cancels with this term. And so all the terms cancel. There's a 1 right in here. There's a 1 plus R to the n minus 1. That cancels with this term. So the only two terms that don't cancel are this term and this term. So we're left with that 1 plus R times S minus S equals 1 plus R to the power of n minus 1. And now we can solve for S. Remember, S is the thing in brackets. It's the thing we're trying to find a simpler expression for. So now we can solve for S. On the left-hand side of the equal sign, we can factor out an S. On the right-hand side, we keep what we have. Notice that this right here just becomes R because 1 minus 1 is 0. We're left with S times R equals 1 plus R power of n minus 1. And that implies that S is 1 plus R to the power of n minus 1 divided by R. So that big expression that's inside the brackets here that we called S is actually equal to this. They're equivalent. And I would agree that what I have circled here is much simpler to write than all of this. So that means that the future value after n periods of this account, where we're putting in P dollars at the beginning of every period, the future value after n periods, it's equal to P times 1 plus R times this thing. Now I'm going to put that in brackets. We got the 1 plus R to the n minus 1 all over R. This is the second time value of money equation. And this is called the future value of an annuity due. This up here is the future value of a single amount. All right, and in the third equation, Well, we want to do the same thing we did here. We want the future value of investing P repeatedly, but instead of at the beginning of every period, we're going to say at the end of every period. So I'm going to copy and paste this. So copy and paste. What is the future value of an account where we invest P at the end of every period into the account? Not the beginning, but at the end. Well, after one period, our account is worth, well, just P, right? Because we put it in at the end of the period and it has no time to get any interest. After 2 periods, our P is worth, this P at the end of the first period grows. We get some interest. But then we also invest P at the beginning or at the end of the second period, right? And it doesn't have any time to get any interest. So the account is just P times 1 plus R plus P. Or if you want to rewrite this, P times the quantity 1 plus 1 plus R to the power of 1, of course. After 3 periods, what's the value of the account? Well, we'll have what we had at the end of the second period in there, which I'm going to write it this way again. We'll have that, plus we'll have the interest on that, plus at the end of the third period, we will put P into the account. So after 3 periods, our account will be worth this much. Now we can combine this term and this term. So RP plus P is the same as just P times 1 plus R. And now what's common? We can pull a P out of all these terms. Or before we do that, we can do another algebraic manipulation. What's common to these two terms? P times 1 plus R. So pull P times 1 plus R out and multiply by 1 plus R. We'll have P times 1 plus R, P times 1 plus R squared. Now, finally, what's common to all 3 terms? A P. And pull a P out, and we'll have 1 plus 1 plus R plus 1 plus R squared. Right? The P times 1 right here is P. The P times 1 plus R is this. The P times 1 plus R squared is this. They clean things up here. So after 3 periods, the value of the account is this. And you can see the pattern that's developing. At the end of 2 periods, it was P times 1 plus R to the power of 1. At the end of 3 periods, it's P p times 1 plus 1 plus r plus 1 plus r to the power of 2. After 4 periods, it's going to be p times 1 plus 1 plus r plus 1 plus r squared plus 1 plus r to the power of 3. Dot, dot, dot. And after n periods, if we used a proof by induction, we would find that the future value of the account is just p times quantity 1, 1 plus r, plus 1 plus r squared, plus dot 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 dot, plus 1 plus r to the power of n minus 1. We're stuck again with this thing in brackets, and we want to find a simpler expression for it. This 1 plus 1 plus r plus 1 plus r squared plus all the way out to plus 1 plus r to the power of n minus 1. What's a simpler expression for this? Well, we already found a simpler expression for this. We set that thing in brackets equal to s up here, and we found a simpler expression for s is right here. We can just go ahead and use that. We did a little trick mathematically. We can just go ahead and use that. So the brackets, whatever's inside the brackets is equal to this. We're going to have p times 1 plus r to the power of n minus 1 all over r and that's our third equation. This is known as the future value of an ordinary annuity. The reason they call it an ordinary annuity is because ordinarily you'll get paid and you can invest your money at the end of a period. You usually get paid, at the end of a week, at the end of a month. You can do your investing at the end of a period. You can't do it at the beginning because you hadn't made any money yet. You hadn't been paid yet, like from your job, for example. So they call this an ordinary annuity. Just for that reason, because ordinarily you would invest at the end. But we could use the logic, well, if you got the money at the end of period 1, then at the beginning of period 2 you could invest it. And so this makes sense up here. At the beginning of every period you're investing. Either way, the only difference here, the future value at the end of n periods, if it's an ordinary annuity, is not quite as big as if it's an annuity due. You can see this part's the same between an ordinary annuity and an annuity due. And both are multiplied by p, but the annuity due has this extra 1 plus r. And the reason is, the annuity due, you invest that p dollars at the beginning of that nth period. And so you get interest on that p dollars over that nth period. But in that nth period, with an ordinary annuity, you invest that p at the end of the period and you don't get any interest on that because you put it in at the very end. So the future value of an annuity due will be bigger than the future value of an ordinary annuity, holding all else constant. Now what I want to do here with the annuity due equation is I want to simplify it. I just want something multiplied by p. So I want to multiply this 1 plus r, or I want to simplify equation 2. So let's do that. The future value of an ordinary annuity, p times 1 plus r times this 1 plus r power of n minus 1 over r. Well, you know what? I suppose we can keep it. We'll keep it the same. I don't want to confuse you. Those are our first three equations. We don't need to simplify anymore. Now, the other three equations in the time value of money can be derived from the future value equations. And now we're going to talk about present value. We're going to talk about present value. What's the present value of P dollars received once in periods from now? If I got P dollars in periods from now, at the end of that nth period, what's that worth to me right now? Well, if I invested P dollars once right now and let it grow for n periods, then at the end of n periods, that P dollars would be worth this much. This was our first equation. So the present value of P dollars received once in periods from now is an amount such that if I could invest it right now and let it grow for n periods and get an interest rate of r every period, it would be worth P. So remember our future value equation. If I invest P now and let it grow for n periods at an interest rate of r every period, then at the end of n periods, my account will be worth this much. What do I have to invest now such that if I invest it now and it grows for n periods at an interest rate of r each period, it'll be worth P? I believe I just need to divide. So if I invest this much right now, and let it grow for n periods, then at the end of n periods, it'll be worth P. So that's our fourth equation. The present value of a future amount is you just take that future amount and you discount it back to today's dollars. And the way you do that is you just divide by 1 plus the interest rate raised to the power of the number of compounding periods. This is the present value. of a future single amount. In finance classes, you'll see discounted cash flows. This concept used. And you're going to be using this formula and repeated applications of this formula in that sort of a context. The idea is you invest, say, $100 now into a project that you expect, so your initial investment, your initial cash flow is negative 100. You expect the project in the first period to generate say $50 of cash flows. In the second period, you expect the project to generate $150 of cash flows. And the question is, what's the net present value of this investment? Well, all we need to do is take these future amounts and discount them back to their present value. The present value of $100 invested right now is just negative 100, plus the present value of the $50 received a year from now. Just discount it back, divide by 1 plus r to the power of 1. And then the present value of $150 received 2 years from now, just discount back to today's dollars by dividing by 1 plus r squared. It's exactly this formula. And then this right here would be the net present value of that particular project with these cash flows. So this present value of a future single amount formula is used all the time in applications in finance. This is just one such example. Let me erase all this stuff so I don't clutter up the board too much. I just wanted to give you an example of where we would use it. All right, the fifth equation is the present value of an annuity due. I gave you the future value of an annuity due in equation 2. If I were to invest P dollars at the beginning of every period for the next n periods, what would the account be worth at the end of n periods? And we found that the account would be worth this much money. The present value of an annuity due is the idea, what amount could I invest right now once? Call that PVN. And if I invest that right now once and let it grow for n periods, it would be equal to this. That's the present value of an annuity due. It's an amount that makes me indifferent between getting this amount right now and investing it once, or investing P dollars at the beginning of every period for the next n periods. And we know that if we did that, the account will be worth that much after n periods. But what amount could I invest right now once, make me indifferent between that and then this? Well, if I invest this amount, we'll call it PVN right now, once, then after n periods, the value of this account would be worth this much, right? This is the future value of a single amount. And if I'm going to be indifferent between doing that and putting P dollars at the beginning of every period for the next n periods, in which case the account would be worth this much, and the question is, what amount PV sub n makes me indifferent between these two options? Well, it's an amount that makes these two ending account values equal to each other. I can either get $1 million right now and put it into an account, and at the end of whatever time I'll have, say, $5 million, or I could put in $100,000 at the beginning of each of the next n periods, and at the end of n periods I will have $5 million. You see, that's the idea of present value. So we solve here for PV sub n. The present value of an annuity due is, we have P times 1 plus R. Now we got to be careful. 1 plus R, the power of n, minus 1, all divided by 1 plus R to the power of n times R. Right? Because we're dividing this side by 1 plus R to the power of n, so we can isolate this variable. We're also dividing the right side by the power by the 1 plus R to the power of n, so that we can isolate the PV sub n. That's equivalent to this. And 1 plus R to the power of n divided by 1 plus R to the power of n, we're just left with 1. And then minus we're just left with 1 over R, sorry. And then minus 1 over 1 plus R to the power of n times R. So I put it into two fractions here. I'm just using the property A minus B over C is the same thing as A over C minus B over C. That's all I'm doing here. But then we can further simplify. We can further simplify this term here. 1 over 1 plus R to the power of positive n is exactly the same thing as 1 plus R to the power of minus n. So we're left with 1 minus 1 plus R to the power of minus n all over R. And I can erase all of this because you all hopefully follow the algebra. This is the present value of an annuity due. This is our fifth equation. And then our sixth equation is the present value of an ordinary annuity. And this is going to line up with our future value of an ordinary annuity. And this one, it's the same derivation as with the annuity due. So we're going to take the future value of an ordinary annuity, which is just P times this, and we're going to say what amount would make me indifferent between putting P dollars in at the end of every period for the next n periods and letting it grow, versus just getting an amount right now, call it this, and investing it once in an account and letting it grow for n periods. Well, the amount that makes me indifferent is the amount such that the two alternative investments would be equal in balance at the end of n periods. And what you're going to find if you do the math, it's just like we did up there. You're just going to find the present value of an ordinary annuity. It's going to look very similar to the present value of an annuity due, but we won't have this extra 1 plus R here. This is equation 6. Present value of an ordinary annuity. You're investing the P in at the end of every period. This is the present value of an ordinary annuity. And so these 6 equations form the basis for everything you will do in time value of money. So we can go and summarize these 6 equations, I suppose, here on one page. And let's do that. That way we have a one-stop shop where we can look to. So the time value of money summary equations. I derived them for you, but our equation 1, future value of a single amount. Take that single amount, invest it once. It grows at a rate of R for n periods. It'll be worth that much. Future value of an annuity due. We invest P at the beginning of every period. At the end of n periods, if the account gets an interest rate of R, every period added to it, at the end of n periods, the account will be worth this much. Future value of an ordinary annuity. We invest P at the end of every period. At the end of n periods, the account will be worth this much. Oh, and I messed up. This one is the annuity due. You're investing up here at the beginning of every period. Here you're investing at the end of every period. And then the present value concepts. Present value of a single amount. Just that future value that you expect to receive discounted back to today's dollars. Present value of an annuity due. Is given by this formula. Don't forget the minus n here. And then finally, the present value of an ordinary annuity is given by this formula. So this is the present value, single amount, present value of annuity due, and the present value of an ordinary annuity. And these 6 formulas, on these 6 formulas are based all the time value of money concepts that you would ever encounter in your courses or in life. They're all based on these 6 formulas. Now let's do an example to illustrate how to use some of these formulas. We're not going to use all of them in this example, but I believe the example will be an interesting example, a real world example, and you will see how important, how powerful these formulas are. There are myriads of examples we could do, but I'll just do one example. Suppose you buy $300,000 house by paying 5% down, and you finance the rest with a, let's say, 30-year fixed rate. What's the interest rate going to be per year? Nowadays, the interest rates are kind of high, so we'll say 7% loan. And we'll assume the bank, they require you to make monthly mortgage payments. At the end of each month, that's how mortgages work. And we'll also assume that interest compounds at the end of each month. And then the question is, what is your monthly payment? Now for this one, we need to reason from the lender's perspective. They're the ones lending the money. They're the ones making the investment. Up here, when we're looking at the time value of money formulas, whose perspective were we reasoning from? The investor's perspective. And in this example down here, who's the investor? It's the bank. So first we need to figure out what's the loan amount. How much are you asking the bank to give you? Well, you're going to pay 5% of the home value down yourself. Your down payment is 5%. Therefore, the amount that you're asking the bank to pay is 95%, or 1 minus the percentage that you're paying. So the loan amount it looks to be is $300,000 times 95%, or $285,000. And in figuring your monthly payment, we reason from the bank's perspective. The bank think of it as they have two options. Option one, they could put the $285,000 amount, they're the ones that had the $285,000. They could put the money once into an interest interest-bearing account. The value at the end of 30 years of that option to the bank, it's the future value. It would just be $285,000 times 1 plus R. Now R here in our formulas is the interest rate per compounding period. So the interest rate they've given us is 7%, but they say interest compounds monthly. So the interest rate per compounding period is this, 0.58%. And we're raising it to the power of n, the number of compounding periods. There's 30 years, but interest compounds 12 times every year. There's 360 compounding periods. Anyway, the bank that could take the $285,000, and one alternative is they could just put it into an interest-bearing account. At the end of 30 years, the account will be worth this much. And I guess we could figure out what this is. We got this plus 1 raised to the power of 360 and then multiplied by 285,000. Which I'm not sure if I did it correctly. 0.07 divided by 12 plus 1 raised to the power of 360 times 285,000, $2,313,201. We'll just round to the nearest dollar. 201.78, we'll just say 202. That's the value of option 1. Alternatively, the bank could give you the $285,000 and require you to give them P dollars. Require you to pay them, and sorry for my tablet, it's messing up, but require you to pay them P dollars at the end of every month for the next 30 years. The key thing is, as soon as they get your P dollars, they put it into that interest-bearing account. And so the value after 30 years of that account is now it's the future value of an ordinary annuity, right? Because they're getting your P at the end of every month, they're putting it into an interest-bearing account. What's the value after 30 years of that account? This is an ordinary annuity. And we remember from the formulas up here, future value of an ordinary annuity is given by this equation. So at the end of the 30 years or the 360 months, the account will be worth this amount. Keep in mind that R in the formula is the interest rate per compounding period. And we said that all along. R in the formula is the interest rate per compounding period, and N is the number of compounding periods. So in this problem, N is equal to 360, because interest compounds once every month, and there's 360 months in 30 years. And the interest rate per compounding period is 0.07 divided by 12 because the annual interest rate is 7%, so the monthly interest rate is 7% divided by 12. So what do you think the bank is going to charge you per month if they decide to give you the money, option 2, versus don't give you the money and put this $285,000 into an interest-bearing account once, option 1? Well, obviously they're going to charge you the amount P that makes them indifferent between these two options. And the amount P that makes them indifferent is an amount P such that the ending value of both options equate. So just set the value of option 1 equal to the value of option 2, and they're going to charge you an amount P that makes them indifferent between these two. In other words, they're going to charge you an amount P that solves this equation. The amount they're going to charge you per month approximately is equal to, and then we can do the math here. Let's get the right hand side here. Let's get what's in the brackets. We'll do 0.07 divided by 12 plus 1 raised to the power of 360 minus 1 divide by the quantity 0.07 divided by 12 gives this. So P is going to be equal to this $2,313,202 number divided by this 1,219.97 number. And so we can do that, or I can get this exact. So 2,313,202 divided by, and then let's go back in our history here. This number right here we want to copy. How do we copy this? Copy. And then we just want to divide that by, and now we just want to paste. And you get $1,896.11 per month. So that's the answer to the question. Every month, the bank's going to charge you that much for the mortgage. And then we could ask the question, well, how much interest will you pay the bank over the 30 years after paying the loan off? Well, that's not hard to figure out. Here's the total amount you're going to give the bank over the 30 years. You're paying this every month, and there's 360 months. This is the total amount you're giving the bank. $682,600, rounded to the nearest dollar. And then of that, so the interest part, how much of this is interest? It's the total you give them minus the principal, minus the loan amount. You're paying off a $285,000 loan by giving them $682,600 over 30 years. So you must have paid this much interest over that 30-year period. $397,600. You paid more interest than you paid principal. And the reason is the interest rate is so high. When you're in a regime where interest rates are really high, like we are now, you're going to be paying lots of interest. We could ask the question, what's the monthly payment if it's a 15-year loan, not a 30-year loan? That would be, to figure that out, you would just change this number here. You change this number to 180, 15 years times 12 months, 180. And this number will definitely go up per month. But then the total interest we would pay the bank over 15 years would be less. We wouldn't pay them this much interest. We wouldn't be paying them this much total. It'd be something less than this. We could figure out how much less interest we would pay over 15 versus over 30 years. It's going to be in the hundreds of thousands of dollars. But anyway, this is just one example of how you can use the time value of money formulas, among many others that we could come up with. And on my channel, I have a video where I just work through problems, just applications of the time value of money equations. This video was more theoretical in that I was just deriving the equations for you, as you could see back here. And then we summarize the 6 equations at the end of the video, or at the end of this part of the video. But in the other videos on my channel, and I guess I could put them in the description below, the links, you can watch videos where I'm just working problems with these time value of money equations. I hope you enjoyed the video and found it useful.